Hello everyone and welcome to another Physics 30 example. This time we have 2 to go through and we're in lesson 5 of unit 4, so we're into electromagnetic radiation, and lesson 5 is Snell's law. This is the law that tells us how light behaves as it passes through different mediums. So in this first example you can see that we have a light ray coming into a rectangular glass prism. So the light ray is coming from air and it's at an angle relative to the side of the glass of 18 degrees. We're told the index of refraction of the glass is 1.54. Of course, we know that the index of refraction of air is close to that of a vacuum, so we'll just go with 1. It's got an index of refraction of 1 in air. And then we're asked to determine the angle of refraction and the frequency of the light in the glass. Okay, so let's break this down a little bit. We're going to do a little thinking first of all on our block. We'll just qualitatively think it through to begin with. So we have this ray coming in to the glass block, and it's incident on the glass block at this normal line. So first things, we just want to make sure that we're really clear about the law, Snell's law. The laws that we use and the ratios that we use for Snell's law are to do with the angle of incidence, which is this angle in here. So the angle of 18, I'm not going to use that directly. I need to use this to then interpret my angle of incidence, and hopefully you can see it's pretty easy. Of course, the angle of incidence is going to be 90 minus 18 degrees. So my angle of incidence is 72. First things first. Okay, I'm going to use this in my equations. Now I'm just going to draw this qualitatively as it comes through the glass block, and I'm going to think of this wave as having a wave front like this, and the side that hits the glass first is going to slow down first. So it's this side of the wave front that's going to slow down first, and that's going to essentially steer or turn the light ray towards the normal line. So hopefully you're getting used to doing this by now. Just qualitatively, we're going to draw this in. It's going to be now closer to the normal line. And again, this is the angle that I'm interested in. This is my angle of refraction. Okay. Just to complete the drawing, once again, if I think about this as a wavelength, now it's the same side of the wave front that hits the air. In other words, it's going to speed up. So this line leaving, or this ray leaving the glass prism, should be parallel to my incident ray. In other words, it's going to bend away from the normal. So let's just qualitatively draw that. Then I'm going to try and draw this parallel to the first line. In fact, I can go ahead and label this angle here, because this angle here is going to be, actually I'll just write the number right in. This angle here is going to be equal to, yes, you got it, the 18 at the beginning, because this line leaving, this ray leaving, is going to be the same or parallel to that ray there. Not that we're going to need that, but I just thought I'd draw that in anyway. Okay, what do we need? Well, we know Snell's law. Let's go ahead and write this out. Snell's law is saying that if you know the index of refraction of one medium, let's call it the incident. Actually, let's go ahead and call it 1 and 2. I'm going to call this 1, index of refraction of 1 over the index of refraction of 2. So I'm going to label, normally we do it in sort of chronological order. This is the first medium that we're referencing. This is going to be the second medium that we're referencing, the glass. So the index of refraction of air divided by the index of refraction of glass is going to be equal to, well, the inverse, or the reciprocal, I guess, of sine theta of 2 over sine theta of 1, which is also equal to the wavelength of 2 over the wavelength of 1, which is also equal to the speed 2 over the speed 1. All of these are possible to use. Notice that the one thing we don't have in here is frequency. Okay, so the other thing we need to think about here is if we need to bring frequency into the picture, then we need to think about our universal wave equation, which is that the speed of the wave is equal to lambda f, or in other words, the wavelength times frequency. So all of these are going to be in play. Let's figure out what we need to do. We might need to do multiple things to figure out the ultimate answer, but we'll just think it through logically. Okay, let's look at the equation. We know, okay, so let's go circling what we do know. We know the index of incidence, the angle of incidence, which is going to be sine theta 1. So we know sine theta 1. Let's put a ring around that. We know, let's get this one here. We know this. We've got that. What we're trying to find out is the index of the angle of refraction. So we're trying to find out this theta 2. Okay. We also know, because it's given in the question, we know the index of refraction of the glass. So I know N2, and then I'm going to go ahead and assume that N1 is just 1. Okay, so clearly this first bit should be straightforward. I'm just using this part of the equation, and let's go ahead and plug in those numbers. We'll just rearrange it to solve for sine theta 2, which is going to be, let's just put a circle around it here. That's going to be this one here. This is going to be the angle 2 right here. So sine theta 2 is equal to, well, I'm going to say N1 is just 1. So it's just going to be sine theta 1, or sine theta 1, multiplied by 1, which is the index of refraction of air, divided by the index of refraction of 2, which we know. So let's write that out as values that we know. So I'm going to go sine 72, because there's my index of refraction of incident. I'm not going to bother with the 1, I'm just multiplying that by 1, divided by 1.54. That's going to give me sine theta 2. So then to get theta 2 on its own, if you plug it into your calculator, do the inverse sine, you get 38.13 degrees. Just making sure my significant digits, it's going to be 38.1 degrees. Okay, so that's the index of refraction, that's the angle of refraction within the glass. Okay, next up we need to find the frequency in the glass. So that means with this guy's in play here, and more specifically we need to know V2, lambda 2, in order to get F2. So how do we do that? Well, we need, let's go and find lambda 2 first. So we need this guy here, lambda 2, which means we are going to, well, we've got lambda 1, there it is, we're given lambda 1 in the question, so we've got lambda 1, and we'll then pair this with our knowns, which is the refractive indexes. So we're going to say, let's do it over here, we'll say lambda 1 is equal to N2 over N1, and that's going to be lambda 2 there. So let's go 630 nanometers over lambda 2 is equal to N2 is 1.54, that's our given, over 1. Which means our lambda 2, this is the wavelength of light in the glass, it's going to be the wavelength of this ray of light here. Lambda 2, if you plug all that in, you're going to get 630 nanometers divided by 1.54, and that's going to be 4.09, some other digits that we'll keep in our calculator, times 10 to the negative 7 meters. Okay, now we can, let's use blue here. Now we're going to say that, we'll say that N2
over N1 is equal to V1 over V2. So just to recap, we found lambda 2, so we're good to go here. Now what I'm trying to do is find V2. Okay, so I'm just going to, again, pick the bits of the equation I need. I know N2 and I know N1, and I know V1 because V1 is the speed of light. So, yeah, let's go with this. We can rearrange this to solve, let's make a bit of space here. We can rearrange this to solve for V2, which is going to be the speed of light in a vacuum, or in air, close enough, over N2, which gives you a speed of 1.948, keeping all those decimal places in your calculator, times 10 to the 8. That, of course, is meters per second. So there we have our, back up, we have our V2, we have our lambda 2. Now it's just a case of getting that frequency. So using our universal wave equation, we can say, so we're going to go V is lambda F, which means F, in this case F2, the frequency of light in the medium, is going to be equal to V2 over lambda 2, which is 4.76 times 10 to the 14, and that's going to be hertz. Okay, so there we have it. That's the frequency in the glass. Okay, example number 2 here. We have a critical angle question. We're given the critical angle to be 24.3 degrees. And now we're asked in sort of a separate question, how much time would it take for light to travel through 5.71 centimeters of a diamond? Include a ray diagram. So crucially here, there's another two-step process. Crucially here, we need to think about what it means to be a critical angle. And hopefully you can recall, this is a straight line, pardon me not using a ruler, and then let's go ahead and put a normal line in here. What it means to be a critical angle is when you go from a dense medium to a less dense medium. So let's go ahead and assume that diamond is the dense medium here, of course, and it's going to be compared to air. So there's air and diamond, okay? And the critical angle is saying that at whatever angle it is, the ray's going to come in, and rather than refract through the glass, it's actually going to, I'll use red here, it's going to travel at 90 degrees, almost within the boundary of the glass. Now, it's important to remember that you will also, at this point, get a perfect angle of reflection as well. And in a sense, the light is sort of taking two different routes. But what we're interested in here is we're not interested in this reflected angle here. We're going to use Snell's law and use this 90 degrees. And so we're given the angle in the question of 24.3. So that's 24.3. And what we can say then, if we're using Snell's law, we're going to say that sine theta, let's go ahead and call this out for its order. This is going to be 1 and 2. Okay, so we're saying that sine theta 1, in other words, the angle that we've been given in the medium that we're traveling in, over sine theta 2 is equal to N2 over N1. Okay. And since we're interested in how much time it would take, we should probably think ahead and figure out which bit of the Snell's law we want to use. If we're trying to figure out how much time, then hopefully you can see we're obviously going to be using our old friend V is equal to D over T. Okay, so we're going to need V, obviously. If we're trying to figure out how much time it takes, then we're going to be using V as well. And so might as well put that into this little equation here. It's going to be V1 over V2. Okay, which ones do I already know? Well, V2 is the speed of light in air. So that's going to be C. I'm going to say that I know that. N2 is going to be 1. I know that as well. And of course I know I'm going to use green. I know my angle of incidence that's given to me in the question, and I also know my angle of refraction because that's 90 degrees. So hopefully you can see I'm going to use the two angles. I'm not going to need this, and I'm going to solve for the speed of light in the diamond, and then I'm going to use that over here to figure out how far it travels, how long it takes to travel in 5.71 centimeters. So let's go ahead, let's carry on. I'm going to say, let's put these values in, I'm going to say sine 24.3 over sine 90 is equal to V1 over the speed of light, which is 3.0 times 10 to the 8 meters per second. Now, sine 90 is also 1, so what I can do, I can say that I can go sine 24.3 multiplied by 3 times 10 to the 8 is my V1, which gives me 1.234, what a coincidence, keeping those decimal places there, times 10 to the 8 meters per second. I'm going to use that up here, so I'm going to say 1.234 times 10 to the 8 meters per second is equal to the distance, which is 5.71. Well, that's centimeters, so I need to convert that into meters. So let's just redo that as 0.0571 meters over the time. And so I'm going to get a value for time, how long it takes to travel in the diamond. If I rearrange and solve, I get 4.63 times 10 to the negative 10 seconds. Yeah, it's really quick, but that's because it's the speed of light. And it's only traveling in a little diamond, although actually 5.71 is a pretty big diamond. So there you have it.